This is the second half of the practice final exam for the spring 2021 semester. So number 12, if you invest $3,000 in an account that pays 9% APR compounded continuously, how much will the account be worth after 3 years? So that's part A. Part B is basically the same thing with the difference of how it's compounded. So in part B, it's compounded monthly, and in part A, it's compounded continuously. And so these two problems, because of this one word, have a completely different formulas. So the formula for the compounded continuously is A equals P times E to the RT. So P, the principal, is $3,000. E to the R is the interest, that's 9%, so 0.09. Years is time, so 3. If we plug that in our calculator, we'll get our solution for A. You should get $3,929.89, rounded to the nearest cent. Okay, so let's look at part B. Part B, since it's compounded monthly, so anything that's not compounded continuously has the following formula. A equals P times 1 plus R over N to the NT. So if it's compounded continuously, it has the formula we used in part A. Any other kind of compounding is this formula. So again, we have the principal is 3,000. The rate is 9%, so 0.09. If it's compounded monthly, that's 12 times per year. So the N is 12 and the T is 3. So when we plug that in our calculator, we will get $3,925.94. Number 13, convert the following logarithmic equations to exponential form. So when you're converting to exponential form, you want to first identify the base. So the base is the subscript right after the log. In part A, there's nothing written there, so it's understood to be a 10. So it's 10, and then remember your exponential looks like this. It's a base raised to an exponent is equal to something else. The way you fill in these boxes is you first identify the base, then you go across the equal sign to find the exponent, and then you go back across the equal sign to get what it's equal to. So 10 to the x power is equal to 2. That's the answer for part A. All right, part B, identify the base. Nothing written there. Since it's a natural log, it's understood to be E raised to the third is equal to x plus 1. All right, and part C, identify the base. We have base 2 raised to the third power is equal to 8. Number 14, write your answer to the following complex number computations in the form A plus BI, where A and B are real numbers. So we have two parts. Part A is a product, and part B is a quotient. So we've got to multiply in part A. So this means we should distribute here. So 3 times 4 is 12. 3 times negative 2i is a negative 6i. I times 4 is 4i, and I times negative 2i is negative 2i squared. Remember that you don't want to have any powers on an I. It's not considered simplified. So I squared is negative 1. So we'll have 12 minus 2i when we combine our I terms here. And then negative 2 times negative 1 is positive 2. So we'll end up with 14, because we can now add the 12 and the 2, minus 2i. Remember that you want to write it with the imaginary part second. The I comes at the very end, or it's not in the correct form and you would not get credit. Now I've seen this happen before. So here we have a product. If they put something else on the final, like let's say they put this on the final, looks very similar to part A, but the difference is there's a plus in between the two parentheses. Remember, this now is a sum, not a product. So the parentheses here really are not important. You just write it without parentheses, and then just combine like terms. So you can combine your two real parts. 3 plus 4 is 7. And then you combine your imaginary parts, and you would get negative I. So make sure you remember that there's not just multiplying and dividing with I. You have to remember how to add and subtract as well. So for part B, we are going to be dividing this, and really what we're trying to do is get rid of the I on the bottom. To do that, when you have two terms here, you have a real and imaginary part, you multiply by the complex conjugate. That means it's the same two terms, but a different sign in the middle. So if you have 1 minus 2i, you're going to multiply by 1 plus 2i. You have to do the same thing to the top and the bottom to keep it balanced. So when we do that, we're going to FOIL the top and the bottom. So we'll have 5 plus 10i plus 20i plus 40i squared over 1 plus 2i minus 2i minus 4i squared. Then we want to make sure we change the I squares to -1. We add up our I pieces. On the bottom, they're opposites, so those just cancel out. So we would get 5 plus 30i, and then we have 40 times a -1. That would give us a -40 over 1. -4 times -1 is going to be plus 4. So then when we continue to simplify, on the top we have 4 minus 40. That gives us a -35 plus 30i over 1 plus 4 is 5. And then we can split that up into the real and imaginary parts. So the real part is -35 over 5. And the imaginary part is 30 over 5. And then you can reduce each fraction. So we have -7 plus 6i. And that would be your solution right there. Okay, number 15. We want to solve the inequality and write your answer in interval notation. So since we have an absolute value inequality, the first thing we want to make sure we do is get the absolute value by itself on one side. It's by itself on the left-hand side, so we're okay there. Then what we want to do is look at what symbol we're using right here. So this is a less than. A less than can be solved in a different way than a greater than. So the way I suggest solving a less than is to make a sandwich. So you rewrite exactly what you have already without the absolute value symbols. And then whatever you have on the right-hand side, so in this case we have a 5, we put a -5 on the other side. This creates a 3-part inequality, and then we just solve that, and that will give us our answer. So to solve, we've got to add 1 to all 3 parts. So this would be -4 is less than 4x is less than 6. Divide by 4. So this would be -1 is less than x is less than, that would be 3/2 if I reduce it. And so here you can see that x is trapped in the middle between -1 and 3/2. And so that is your solution set. -1 to 3/2, both with parentheses because there was no equal to sign underneath it. So that's the answer. Remember that the greater than is solved in a different way, so you need to go back and remind yourself how to solve an absolute value inequality if you actually had a greater than instead of a less than. Okay, so 16, solve the equation. So what we want to try to do here is condense the left-hand side so that it's 1 log. We can do that by remembering the quotient rule. So if you have a minus, we have 2 logs with the same base, so we can write log base 7. The minus is going to indicate that we have a fraction. Whatever has a positive in front of the log, so right here, there's no sign, so it's understood to be positive, that goes on the top, so that x plus 1 is going to be in the numerator. If there's a negative in front of the log, then that stuff goes on the bottom. Okay, so we have log base 7 of x plus 1 over x equals 2. Now we have 1 log in our equation, so we're going to write this in exponential form and solve. So the base is 7, so it'll be 7 raised to the second power is equal to x plus 1 over x. So 7 squared is 49. We always want to try to get rid of the fractions, so we will have 49x is equal to x plus 1. We can subtract x from both sides, so we get 48x is equal to 1. Divide by 48. And so now x is equal to 1 over 48. So what we want to do is make sure that this checks out. So we have 2 different things we're taking the log of. We are taking the log of x plus 1. So we need to check and make sure that x plus 1 is greater than 0. Okay, so we're going to plug in our answer, 1 over 48. 1 over 48 is going to be a positive number. That's going to be greater than 0, so that checks. We also need to check what else we're taking the log of in our original equation, and that is x. So we need to check and make sure that x is going to be greater than 0. If we plug in our x, 1 over 48, that is greater than 0. So it checks in both cases, so this is a valid solution. Number 17. An account with an initial deposit of $6,500 earns 7.2% annual interest, compounded annually. Okay, so that's, remember, how it's compounded decides which formula we use. How long will it take for the account to be worth $7,000? So since it's compounded annually, we're going to start by writing down that formula. Okay, and now we're going to fill in what we know. So it says at the end that the account is going to be worth $7,000. So that's the A value. That's the amount at the end. The principal or initial investment is $6,500. The rate is 7.2%, which is 0.072. It's compounded annually, so that means once a year. And we don't know how long it's going to take. That's what we're trying to find. Okay, so let's simplify this. So we can simplify what's in the parentheses. So 0.072 divided by 1 is just 0.072. And then added to 1, that'll be 1.072. And 1 times t is just t. So we can simplify it like that. Now, since we have our variable in the exponent, this is an exponential equation. So we're trying to get the exponential part by itself. So what's raised to the t power? Just this 1.072. So we want to get what's in the red box by itself. So that means we need to undo the 6,500. So we're going to divide both sides by 6,500. So 7,000 divided by 6,500, if I reduce that, we're going to get 14 over 13. is equal to 1.072 to the t power. Now I can write this in logarithmic form. So the base, we want to identify the base. The base is 1.072. So this is going to be the log base 1.072 of 14 over 13 is equal to t. And so now you can just put that in your calculator and figure out what it is. So t to the nearest, let's say thousandths place would be 1.066. And it's time, so it's years. Okay. Number 18, here's another logarithmic equation. We're going to solve this equation. So we have multiple logs. We're going to condense each side. So on the left-hand side, we will have the log. Since it's a plus, we're going to be multiplying what's in here. So this will be 2x squared. What we want to do here first is, in order to just get the log without a number in front, without that coefficient, we're going to use the power rule. So this would be the log of 5 squared plus the log of x. Now we're ready to condense that side as well. So we'll have the log of 2x squared is equal to the log of 5 squared is 25 times x. So we can now multiply these. Now that we have one log on each side, those are going to undo each other. So 2x squared must be equal to 25x. Since we have a quadratic, we're going to move everything to the same side and set it equal to 0. So 2x squared minus 25x is equal to 0. Now we can try to factor, or you can use the quadratic formula. So I can factor out an x. So that'll give me 2x minus 25 left. So that means x is 0, or 2x minus 25 is 0. That means 2x equals 25, or x equals 25 over 2. So we need to check both of these. So we're going to go through our original equation. So first I have log of 2. Well, that doesn't have a variable, so I don't have to check that part. Then I see log of x squared. So I need to check to make sure that x squared will be greater than 0. So I'm going to check 0 first. So I need to make sure x squared is greater than 0. So if I plug in 0, 0 squared is 0. So is 0 greater than 0? No, it's not. So that does not check. That means that 0 is not a valid solution. All right, I'm going to check my other possible answer. So 25 over 2. So x squared has to be greater than 0. So if I square 25 over 2, that's going to be positive still. So that checks. Okay, then I go down the row, and 5 is what I'm taking the log of next. That's not a variable. I don't have to check that. Then I see x. So I need to make sure that x is greater than 0 when I plug in my supposed solution. 25 over 2 is in fact greater than 0, so that is a valid solution. So the only answer that we have for this problem, because it's the only one that checked, is 25 over 2. Use the rational zero theorem to list all possible rational zeros for the polynomial. So you don't have to find the actual zeros, just the possible zeros. To do this, you have to use the ratio of p over q. P will be all the factors of 27, and q will be all the factors of 3. So the factors of 27 are 1, 3, 9, and 27. So it's all whole numbers that multiply to get 27. And then the factors of 3 are 1 and 3. So now what you want to do is make a list of plus or minus all fractions that you can make with the p on top and the q on bottom. So plus or minus we're going to start with a 1 for p and put 1 over 1, 1 over 3. So now we've done the 1. Now we're going to do the 3. So 3 over 1 or 3 over 3. So that one's done. So again, we're doing this, 3 over 1 and 3 over 3. We're doing that for each possible p. So now we've got to do the 9. So 9 over 1, 9 over 3. And then 27 over 1, 27 over 3. All right, so that's every possible combination. Now your job is to simplify this list. So 1 over 1 is 1, 1 over 3, 3 over 1 is 3, 3 over 3 is 1. That's already on the list, so I'm not going to write anything down more than once. 9 over 1 is 9. 9 over 3 is 3. That's already on the list. 27 over 1 is 27. 27 over 3 is 9. That's already on the list. So here are all of my possible rational zeros for the polynomial f. Find an equation for the quadratic function graphed below. All right, so for this one, you have to notice that, first of all, it's a quadratic, and it even tells you that. So you know that the general form, let me make this a little bit smaller here. Okay. So the general form for a quadratic is f of x is equal to a times x minus h squared plus k. And in fact, you don't have to put f of x, you could put y if you want, because we're going to end up using a y value. So here's what this looks like. Now you have to figure out what to plug in all this stuff. So your goal is to find hk. Remember that hk is your vertex. So you'll use your vertex. In this case, that is a maximum, so it's up here. And then you have to find some other value, some other point for x and y. So you want to try to find one that's going to be an exact point. It's easy to tell what it is. So let's first look at the x and y axis and label all of these dashes that are not labeled. So 0 to 2. So if you're not sure how to label these, what you can do is count how many empty spots or how many jumps you have. So from 0 to 2, you're moving up 4 units. So 1, 2, 3, 4. So what you want to do is take the difference here, so 2, and you want to divide that by 4. So if you do that in your calculator or if you do it in your head, you'll see that you get 0.5. That's how much you should be adding each time you go up, 0.5. So again, you take whatever distance this is, so 0 to 2 is 2, you put that on the top. Then you count how many times or how many intervals you have between those two numbers. So between 0 and 2, we have 1, 2, 3, 4 jumps up, so we divide it by 4. We got 0.5, so that's what we have to add each time we move up 1 notch. So this 0 plus 0.5 is 0.5. Then if we add 0.5 to that, we get 1. If we add 0.5 to that, we get 1.5. And if we add 0.5 to that, we get 2. So by doing that, you can then label all of these accurately so you'll know where your dot is. So the dot on the y-axis is at 3. And then the same thing is going to be true for the x-axis. Okay, so label them to make sure you know what your ordered pairs are. So for the vertex, it's at 2, 3. Okay, so now we can find another point. Now that you have them labeled, you might be able to see that this goes through at a good point to choose. This goes through at 1, 1. So x, y, we can have as 1, 1. So that's what we're going to plug in our equation over here on the right. y is 1, a is what we're trying to find out, x is 1, h is 2, and k is 3. And now we're going to solve for a. So we'll have 1 equals a times 1 minus 2 is negative 1. Negative 1 squared is positive 1. 1 times a is just a. And then if we subtract 3 from both sides, we will get a is equal to negative 2. Once you find a, you're going to use your vertex and your a value to write your final answer, your final function. So your final function or your final answer would be f of x equals negative 2 times x minus h, which is 2, plus k, which is 3. So that would be the equation of this quadratic function. Okay, so 21, we're going to find the population of honey badgers with a given function. T is given in years. To the nearest whole number, what will the population be after 4.5 years? So they're giving you the function, they're telling you the t, so you just plug it in and solve. So all you're going to do is plug in 4.5 for t, and then get the answer in your calculator. When you plug it in, let's see, it says to the nearest whole number, so make sure you round appropriately. Let's see, you will get 36.8. So to the nearest whole number, that would round up to 37. So 37 honey badgers. Okay. So that is key. Make sure you don't lose points on the different problems for not rounding appropriately or giving your answer in the correct form. So make sure you always read the directions carefully about how to round or how to write your answer so you don't lose points for something like that. All right, the final question. So number 22. Identify the location of all zeros of the polynomial graphed below, and then determine if the multiplicity of each zero is even or odd. All right, so a 0 is just where it crosses the x-axis. So you're just going to identify all the places where this graph crosses the x-axis. So that could be simply just putting dots there. That's absolutely fine. So you've identified them. Now in part B, you want to decide if the multiplicity is even or odd. Well, probably you learned about multiplicity 1, multiplicity 2, and multiplicity 3. So then all you have to figure out is the number even or odd? So for this first one, the 0 at 1, you can see that the graph approaches the x-axis and then bounces back. That's an indication of multiplicity 2, right? Multiplicity 2. 2 is an even number. So you would say that this has even multiplicity. Okay. Or the 0 at 5, this goes directly through the x-axis. So this was an indication of multiplicity 1, and so 1 is odd. So you would say odd multiplicity. And that's all you have to do on that one.